Hi, I'm David Zuckerman. I'm a professor of computer science at the University of Texas at Austin. That's the UT Tower behind me. I got interested in theoretical computer science because it's a great way to apply interesting mathematics to compelling questions. So the theory of computing relates to many disciplines, and there are many simply stated challenging problems. My focus is on randomness and computing, mostly pseudo-randomness, and you'll get a flavor of that today. So let me share my screen. And let me start from the beginning. So again, I'm going to discuss randomness and computing. Maybe the most basic thing in randomness is random sampling. So just think about flipping a coin. Let's say we flip a fair coin 1,000 times. Well, the number of heads will be 500 plus or minus 35 with 95% certainty. And if you do it with n coins, you'll get n over 2 heads plus or minus square root n heads with 95% certainty. So this converges to fraction 1/2 very quickly. And this is useful not just in computer science, but more generally. So in polling, for example, there was a recent Gallup poll asking people if they want to abolish the Electoral College. And here they just asked 1,000 people, and with 95% confidence, they can get the right answer plus or minus 4%. So the United States has a huge population, 300 million or more, but you can choose a sample size independent of the population. So in fact, it wouldn't matter if the US had a population of 300 trillion, still a sample size of just 1,000 would suffice to get high confidence of the right answer to within a small margin of error. And this idea is useful in computer science. So for example, suppose we want to calculate the area of some region. And this is a very complicated region that we can't get our hands on. We don't know how to integrate anything here. All we can do is tell whether or not a point is in the region or not. So let's say that's the case. And we also know that this region is contained inside some square, say. Well, we can choose many random points in the square, and we can compute the fraction r of these random points that lie in the region. And we can take as our area estimate of the region r times the area of the square. This is very natural. And with high probability, it will give a good estimate. So this idea is used throughout computer science. There are much more sophisticated random sampling techniques that are used to approximate various quantities. So if you want to approximate the volume of a region, sometimes the situation is not as simple as I said. You can use more complicated techniques to estimate the volume of a region. You can also use it to estimate an integral, which is similar to a volume. Or you can use it to approximate the number of solutions to an equation. It's also useful in load balancing. So here you may have a computer that has many cores and jobs come in. How do you distribute jobs to the cores? Well, a natural thing is actually just to distribute them randomly. And this balances out the load pretty well. In practice, randomness is used a lot in Monte Carlo simulations. So these are simulations of complex systems that are done on the computer. So for example, the economy, or the weather, or molecular interactions can be simulated using sophisticated models. And these models often have random components. So these random components can model actual randomness, for example, coming from quantum mechanics, or just complex phenomena. It's sometimes convenient just to model them as randomness. Randomness is really useful in cryptography. So if you want to buy something online, you're using randomness. And it's really essential for secure communication. Because if the secret key is not random, then the eavesdropper could learn it. So it's crucial that, that cryptography uses high quality randomness. So outline of this video, I want to discuss randomized algorithms with an example. Then I'll discuss complexity classes RP and BPP. And then we'll discuss the question of whether BPP equals P. And this will lead to a discussion of pseudorandom generators. In this first video, I'm just going to talk about randomized algorithms, and I'll introduce RP. Just as a quick refresher, probably all of you know this, but if I say a random bit, I just mean that X takes on the values 0 or 1 with probability 1/2. And if I say a random integer from 1 to 100, I mean that for all I, the probability that Y equals I is 1 over 100. And if I talk about independent random bits, I mean that for any I conditioned on all the other Xj, Xi is still a random bit. Or equivalently, if you take any 100-bit string, the probability that x1 through x100 equals this fixed 100-bit string is exactly 1 over 2 to the 100. Okay, so now let's look at a randomized algorithm as an example. So here we have this example. Does 12 to the 2,000,001 plus 7 to the 442 equal this right-hand side? So this is, these are pretty big numbers. The natural algorithm is to multiply it out and add. The problem with that is that it's very inefficient. You need to store 2 million digit numbers. These are quite big and not easily stored in a computer. And in general, deciding whether a to the b plus c to the d equals e to the f plus g, if you just do it naively in this way, this is going to take exponential space and hence exponential time. So this is not a good way to do that. Is there a better way? Well, it's natural. Let's start out looking at this specific example. If you look carefully, you can actually see that these are not equal without doing any complex calculation. Why? Because the left-hand side is odd. It's an even number plus an odd number. And the right-hand side is even. It's an odd number plus an odd number. Well, is that just a cheap trick? What if both sides are even or both sides are odd? What can you say then? Well, the insight is that odd or even is the remainder modulo 2. But why is 2 so special? What about looking mod other numbers? So this hints at the randomized algorithm. To test if the two sides are equal, we'll just pick a random number between 2 and some pre-specified bound. Don't worry too much exactly what this is, but note that it's a reasonable number. It's logarithmic in the quantities we're interested in. So it's not too big. So in our example, it's less than 15 million. You might think, well, oh, 15 million sounds big. But remember, 15 million is just 8 digits. It's easily stored in a computer. So it's really not that big. So we'll pick this random number and we'll compute the remainder modulo r. And we can do this efficiently. How? Because we do have to, it is a little tricky in that we have to raise numbers to very large powers, but we can do that by repeated squaring. So if we have to raise a number a to 2 to the k, we'll just square the result k times. And this requires just k multiplications instead of 2 to the k. And this is how we're going to get polynomial time. We'll only keep track of the remainder modulo r. So for example, if we want to compute 7 to the 5th mod 41, we write 7 to the 5th as 7 squared times 7. So this is 49 squared times 7. 49 is congruent to 8 mod 41. So we get, this is congruent to 8 squared times 7. 8 squared is 64, which is congruent to 23 mod 41. And then we just do 23 times 7, which works out to 38 mod 41. Okay, now, of course, if the two sides of this equation are equal, then the remainder mod r of both sides are equal. And the interesting thing to show is that if the two sides are not equal, then the remainder mod r is not equal, with probability at least a half, or even bigger than half. So this error probability, and note that we can improve the error probability by repeating. So suppose we start with error 1/2. If we repeat it k times, the error becomes 2 to the minus k. Because in order for an error to occur in this whole process repeated k times, an error has to occur in each of the k runs. And the probability of an error occurring in each of the k runs is at most 1/2 to the k. So let me sketch this lemma. So we let m be the difference of the two sides. So we want to see if a to the b plus c to the d equals e to the f plus g. We'll let m denote the difference in absolute value. And now we want to test if m equals 0. Well, again, m equals 0 is, there's nothing really to prove. If m equals 0, the two sides are equal. The remainder mod r is equal. The interesting case is if m doesn't equal 0, we want to show that the remainder mod r on both sides is not equal with decent probability. And that's equivalent to showing that m mod r is not 0. So the key claim is that there aren't too many primes that divide m. In fact, there are most log m primes that divide m. Why is that? Well, if p and q are different primes, both dividing m, then their product divides m. More generally, if there are distinct primes dividing m, then their product must divide m, which means if m is bigger than 0, that means that m is at least the product of all these primes. And each prime is at least 2, so this is actually at least 2 to the r. And that's it, we're done. We've shown that m is at least 2 to the r. Taking the log base 2 of both sides says that r is in most log base 2 of m, and that's what we wanted to show. This notation LG stands for log base 2. Okay, so let's analyze a slightly different algorithm. In fact, we could use this algorithm instead. It was just simpler to state the other algorithm. Here we'll choose a random prime among the first two r primes. Call this random prime p, and we'll test if p divides m. So the probability that p will divide m, well, there are most r primes that divide m, and we're picking p among two r primes, so this probability is at most 1/2. And note that p divides m is equivalent to a to the b plus c to the d congruent to e to the f plus g mod p. Okay, so this is exactly what, so this corresponds to the algorithm that we were looking at before, except now we're picking a random prime instead of a random number among the first so many numbers. And this is, so this can all be done in randomized polynomial time. Okay, so that's a sketch of the algorithm. And randomized algorithms are useful in many different areas. So we've just looked at algebra and number theory. I just showed you this algorithm for equality testing. It's also useful in testing whether a number is prime. I'll give you a flavor of that in the next video. It's useful in factoring polynomials for polynomial identity testing. It's useful in graph theory for min-cut, shortest paths, minimum spanning trees. As I mentioned earlier, it's very helpful in approximate counting. You can compute the volume or approximate the volume in this method. You can approximate integrals. You can approximate the number of solutions to equations, the number of satisfying assignments, the permanent. You can also approximate optimization algorithms where you want to approximately optimize some quantity. So as you may know, stochastic gradient descent is a randomized algorithm that's extraordinarily useful in machine learning. most of the advances that you see coming out in artificial intelligence trace back to the effectiveness of stochastic gradient descent. It's also useful in combinatorial optimization algorithms such as max-cut or max-sat. And there are many more that I don't have time to describe. So these randomized algorithms are often much faster and are simpler than known deterministic counterparts. So let's try to view them in a complexity theoretic framework. So let's discuss randomized polynomial time. We say that a language L is an RP for randomized polynomial time if and only if there's a randomized algorithm. I'm writing it as there exists a probabilistic polynomial time Turing machine, which I'll define in a minute. So if and only if there exists a probabilistic polynomial time Turing machine M, such that if a string is in the language, the probability that M accepts it is at least a half. And if the string is not in the language, M will never accept it. It accepts it with probability 0. So a probabilistic Turing machine is just a Turing machine that can access random bits. So just think of it as a randomized algorithm. It's convenient not to think of Turing machines for now. You've seen earlier that Turing machines are equivalent to maybe easier models to think about, like the RAM model. But you can think about your favorite model and think about a randomized algorithm in that model. So for example, unequal is an RP, where unequal is a set of 7 tuples such that a to the b plus c to the d doesn't equal e to the f plus g. Because remember, if we take this mod a random prime, with probability at least 1/2, the two sides are different. So we can output unequal. And if the two sides start out being equal, if we take it mod a random prime, they'll still be equal. We'll never say they're unequal. Okay, so it's unequal that's in RP. This is not a symmetric definition. So you need to check. It's not equal that's in RP, but unequal. And RP, of course, contains the class P, because if M were a deterministic algorithm deciding L, well, then M would accept with probability 1 if W is in L, and with probability 0 if W is not in L. So it would satisfy these conditions here. It's also in NP. Why is that? Well, certificate that W is in the language is just some random string that causes M to accept. So in our example, a certificate is some prime that gives a to the b plus c to the d mod p different than e to the f plus g mod p. In fact, in that original example, p was just 2, and I showed you that the left side was odd and the right side was even. So that was sort of an example of an NP certificate. So in fact, you could think of RP as NP where there are lots of witnesses or lots of certificates. Right, with probability 1/2, if you just pick a possible certificate at random, with probability 1/2, it will be a valid certificate. So that's what RP is. Another way of thinking about it is that NP corresponds to, instead of at least a 1/2 here, greater than 0 here. So for example, if language L was sat, if we just picked a random assignment, if it's satisfiable with probability greater than 0, this will be a satisfying assignment. But if it's unsatisfiable, it will be a satisfying assignment with probability equal to 0. Okay, so it's very it's very related to NP. Okay, so that's the end of this first video. In summary, we've seen an example randomized algorithm that works very well. We don't know how to solve it deterministically, and we can capture randomized algorithms by this complexity class RP. Okay, so we'll continue here next time.